Hi, welcome to my channel, JaberTime. Today I'm going to talk about a few things. The main parts are on this slide, as you could see. Composition of functions. And it comes in different ways, but this is the main one right here. We're going to talk about it in detail. One thing that is important about composition functions, which is the domain. You have to be careful when they ask you for the domain of f of g of x. And I'll show you how in a good example. We're going to end the video with how do you decompose a function? How do you take it back if it's given to you as one package? How do you break it down to two functions? Which one is f, which one is g? Of course, there is sometimes more than one way to do it, but we'll show you how. Okay, let's get into it. Composition of functions. For two functions f of x and g of x with real number outputs, we define new functions. And those are quick ones: the sum, the difference, the product, the quotient. And of course, in the quotient, you have to be careful that the domain cannot equal to 0. Here's a practical one. C of t of d, where c is cost. The function c of t gives the cost c of heating a house for a given daily temperature in T degrees Celsius. The function t of d, the inside part, gives the average daily temperature on day d of the year. What does that mean? For any given day, we have a temperature that corresponds to it, and then we have a cost for that. The cost will be c as a function of t of d, which means that the cost depends on the temperature, which in turn depends on the day of the year. Thus, we can evaluate the cost function at the temperature t of d. C of t of 5 will be the cost for the temperature on day 5. T of 5, the inside part, is the temperature on day 5. So we find the day, locate the temperature, let's say from the recording or the chart. Once we know the temperature, we could tell the cost. So it starts here, then goes to t. Then that becomes an input for another function called c. So we have day 5, we have t of 5. T of 5, whatever the value is, will be the input for the newer function, which is c, and that will read as c of t of 5. And that also explains the cost for the temperature, c of t of 5, and t of 5 is the temperature on day 5. Find and simplify the functions. We are looking at subtraction, product, and quotient. We'll take care of them, and for the quotient, I'll have more work for it. And as I said, like usually, we have to be careful on the quotient ones. For the subtraction ones, we just subtract normally. G minus f of x will be g of x minus f of x. I have g, x to the second minus 1. Subtract f of x, which is x minus 1. Apply the distributive and make sure that you apply the negative to the negative, becomes positive. These numbers cancel, negative 1 and 1. And now I have x squared minus x. For the second one, we have a product. All what I need to do is display what is f of x and g of x, and use the distributive property as one idea. Rearrange if you want, you don't have to, and that should do it. Let's look at the last part, which is the quotient. Once you have it, you need to divide g of x by f of x. But what is g of x right here and f of x? But notice that the numerator, which is g of x, is actually a difference between two squares. We call it in math like a squared minus b squared. which we could factor to a minus b times a plus b. But what happens if you do that? X minus 1 cancels. Well, of course you could cancel as long as x is not equal to 1. Because if x equals to 1, that becomes 0 over 0, which is undefined. So you have to state that. So the simplified form of the quotient g over f is a straight line with a slope of 1 and a y-intercept of 1, but with the condition that x cannot equal to 1. So the domain is all real numbers except 1. And the problem is not asking me to graph, but I think it helps a lot to understand more using graphs to support the concepts. So the domain is all real numbers except 1. Now, one more time, we're going to talk about the composition of functions. I'll go a little bit fast to save you some time, but that will help. When the output of the function is used as the input of another function, that's what we call it, composition of functions. For any input x and functions f and g, this defines a composition function. We write it as f of g of x, and that's the formal way. We read them the same way, f of g of x, f of g of x. And that also says exactly what I was reading right here. So x is the input of g, and g of x becomes the input of f. Now, something that you have to be careful, as I mentioned on the first slide, is the domain. To find the domain, there is two things that you have to pay attention to. And after that, I have a good example that I'm going to go through it with you. The domain of the composite function f of g is all x such that x is in the domain of g, of course. If it belongs here, I could continue. If it doesn't belong here, I cannot use it. That is clear. So start from here. And now, what the second statement says is the following. Now, let's say I could plug in 7 here, and g of 7 is 10. But 10 cannot be plugged in f. That causes a problem. So, what I'm trying to say is the outputs of g of x, they have to agree with the domain of f. If they don't, we have to take them out. That's exactly what I'm trying to say. And here's the answer. G of x, the output, is in the domain of f. They have to. Just a quick note. This composite and this composite are not the same. In general, they are not the same. The product and f of g of x are not the same. Okay? After this slide, I'm just going to show you a good example about the domain in detail. Here's an example about the domain. To find the domain of f of g of x, where f is 5 over x minus 1 and g of x equals 4 over 3x minus 2, the domain of g of x, looking right here, consists of all real numbers except 2/3, because 2/3 will make the denominator 0. You could solve for it in steps. 3x minus 2 equals 0. Add 2 to both sides, divide by 3, and you get 2/3. So we're not allowed to use 2/3 because that's going to cause the denominator here to be 0. Okay, this one is done. The second one is something that you have to be careful with. Now, likewise, the domain of f consists of all real numbers except 1. Looking at f right here, I could plug in anything. I could plug in 2, I'll get 5 over 2 minus 1. I could plug in 10, 5 over 10 minus 1. But I can't plug in 1. 5 over 1 minus 1 will be 5 over 0, so which is undefined. That means once you take care of this, the outputs of this that you need to plug them in here, because f comes after g, cannot be 1. So you take the restrictions from here, which is in the domain of g, and you take from its outputs the value 1, because that's going to cause a problem right here. So we need to exclude from the domain of g of x that value of x for which g of x equals 1. So now we do some algebra steps. This is my g of x. I don't want it to be 1. So we solve to see what will take it to 1. Cross multiply. I have 4 equals 3x minus 2. Simplify, add 2 to both sides. 6 equals 3x divided by 3. And I get x equals 2. So x equals 2 right here will provide you with 1, but you cannot move on. So the domain of f of g is the set of all real numbers except 2/3 and the number 2 that gives me 1 here, as we agreed on from the beginning right there. This means that x cannot equal to 2/3 and cannot equal to 2. We can write this in an interval notation as from negative infinity to 2/3 union, from 2/3 to 2 union, from 2 to infinity. Now, determine whether composition of functions is commutative. I have two functions, 2x plus 1 and 3 minus x. We're going to do it both ways. F of g of x will be f of g of x. I'm writing it differently, but we read it the same way. Instead of g of x, I'm going to write 3 minus x. Now what does f do? Anything we have as an input, which is x, we need to multiply it by 2 or double it, then increase the amount by 1. So let's multiply this by 2 and increase it by 1. Simplify, and that's my answer. Of course, I have 6 and 1, which is 7. 7 minus 2x is the final answer. Let's go the other way around. G of f of x. So who's first? F. We take care of f first. We inside put 2x plus 1. But what does g say? Anything I give g, I have to give it a minus sign and add a 3. I have to go 3 minus that amount. Here's 3 minus that amount. Distribute the minus sign. Simplify, combine 3 and negative 1 to positive 2, I mean. And that's the answer. Now notice that 7 minus 2x does not equal to minus 2x plus 2, which means the operation of function composition is not commutative. This is an example that contradicts that, so it's not a rule. If it's a rule, it should apply all the time. We call it in math counterexample. One example will do it to verify that it doesn't work, or it's not a rule that we could depend on. Using the following table, evaluate f of g of 3 and g of f of 3. Okay, let's slow down and look at the numbers slowly. Let's look at the first one. F of g of 3. Well, I need to locate 3 as an x value and find its output in the g. Here's g and here's 3. The output in the g function is like a the table is like 2 in 1. So now we're looking at g only. When x equals 3, g of 3 equals 2, and that's what we have. That becomes the input for my new function, replacing g of 3 with 2, because that is the output of 3 under g. Now I need to look at 2 as an input for the function f. 2 under the function f will take me to 8. So f of 2 equals 8, and that should do it. Let's look at the other way around, which is g of f of 3. Now we need to look at 3 as my input. 3 as an input. Apply f. I will be at 3 still. F of 3 is 3. That's my input now. I need to apply g. So from 3 I go to 2 under g, and that should do it. Okay? Evaluate f of g of 1, and I have two graphs. One of them is f and the other one is g. So first we're gonna locate 1, go to the graph of g, which is the first graph, locate its output, take that as an input in the function f. Let's take a look. This is my g. I'm locating the 1, and the output is 3. Now g of 1 is 3. I take 3 in the function f, that's my input for the function f, and reach out to read its output, which is 6. F of 3 is 6. 1 took me to 3. 3 under the function f took me to 6, and that should do it. Given the function f of t equals t squared minus t and g of t equals 3x plus 2, evaluate f of g of 1. We're going to take 1 right here. Once we're done, that will be the input for the new function f. G of 1 equals 3 times 1 plus 2, which is 5. Now this is this right here. Now I have f of 5. Take 5 here, square it, subtract 5, and that should do it. 20. How do you break down a function given to you already as two functions, one after the other? This says f of x equals square root of 5 minus x squared. And we need to decompose and make it two functions. Well, first we'll start with x. Let's call the function, the first function, h, and that will do the following. We'll square it, give it a minus sign, and add 5. In other words, we're going to read it as 5 minus x squared. Once we have this, we're not done. We need a square root. So we'll apply the square root. Applying the square root from here to here, the only thing that shows up is the square root. So that's what g does. So h of x will be working inside first. It's almost like order of operations. Where do you start? I start working inside, then I'll take care of the square root. And g will be the square root. So g of h of x will be g of 5 minus x squared, which is the square root of 5 minus x squared. That's my g, that's my h, and that should do it. It's about 80 minutes. I'm doing my best not to make it 30 or over 30 minutes. And it looks like it's working. Hopefully my videos will be like 15 minutes or less in the coming sections. Thank you very much, and I'll see you in the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.